And when it dies, it makes calcium carbonate sand. And so it may be, and appears to be, a major source of sand for the Maui Nui Island complex. So the objectives of that scope of work during that year were to document the distribution of Halimeda Kanalawana meadows, study their survivorship and seasonal abundance, examine their resilience to disturbance, study their general physiology, how does it vary over depth, how does their growth differ, and continue documenting organisms using the meadows as habitat. What I'm going to focus on right now is just give you some of the seasonal trends that we saw and were able to collect during December 2007, looking at survivorship and seasonal abundance, mainly survivorship or lifespan, looking at the resilience of Halimeda to disturbance, which have direct management implications, and studying the physiology, or in this case, growth rate of Halimeda across a broad depth gradient. And the value of this is, again, this whole broad depth gradient. Oftentimes, we're limited to less than 20 meters in a lot of our studies because that's what we're limited to do in terms of convenience or time limitations with air consumption and logistics. It's the name of the game. But with these Halimeda meadows, the majority of their abundance are in these deeper depths. And so to do a study at 10 meters or 15 meters, what's the implications of that if we're really truly trying to understand primary productivity or the distribution of a species? And so this is why we picked multiple depths and also seasonal perspective to look at this assemblage. And that's the real importance of this data set. So one aspect of it is Halimeda lifespan. So you go out to these meadows and you see this expansive green. And your first thought is, oh, there's just a lot of it. I'm sure it's always here, or maybe it comes and goes. But how old is an actual plant? With algae, we typically think of them being fairly short-lived for a green alga. You think of large kelps, they've documented them living up to 7 to 8 years. But how long do these things, this tropical calcified green alga, live? And what we found is, based upon tagging of some individuals, some of them have lived over 3 years now, which means that I can't finish my PhD until I figure out how these things die. But they just keep going. So some of them have been fairly short-lived, like I've tagged some and they've lasted 8 months or 12 months. But other ones, over 3 years. And so what this suggests is that while there are some short-lived plants that come and go, there's also a number of very long-lived plants. And if you go into the meadow and you see the amount of encrusting organisms growing along the base of the plant, you're like, oh, okay, this kind of makes sense. So they're fairly long-lived, some of them. Another aspect of what we did is we did looking at the resilience of Halimeda to disturbance. And so we did a clearing experiment. And if you're to go in one of these meadows, they're often targeted for anchoring because it's soft sediments. A little bit better probably than coral. But what's the consequence of this? If you have a large cruise ship anchor anchoring a Halimeda meadow and ripping out a large chunk of it when it gets pulled up, what does it matter? If it goes along the top and it rips off the top of the plant, is it just going to grow right back, or does it take a long time? If you remove the entire plant, does it make a difference? These were some of the questions we were interested in answering. And so what we did is design this experiment, clearing 1/4 meter square areas. And we had controls where there was no manipulation to the plants inside the quadrat. We had cut plants where what we did is just remove the upright thallus just above the first segment, the first few segments above the plant. So it was sort of like to mimic sort of cutting out the top of the photosynthetic portion. And then clearing, so taking out the whole kit and caboodle, the thallus and the holdfast, this lower section that anchors the plant into this sediment, removing that entire section. And so this is the experiment that we designed. And we did this in 5 quadrats for each treatment over a 50-meter area. And so, for instance, April 3rd, 2006 is when we first did it. And you can see, so this is a controlled treatment, so no manipulation, and we measured the recovery of numbers of individuals and also canopy height of the individuals. Here's an example of the cut treatment, so again, just sheared off right at the top, all the individuals within that area. And then a cleared section with all of the thallus and holdfast removed to the best of our abilities to getting everything out. And what we saw after 110 days, and this is in July 23rd, 2006, no difference in the control. The cut treatment rapidly regrew, and we think that's just from the initial holdfast. And then, but the clear treatment, this is the most that came in any quadrat, very slow to recover. So what I wanted to do is to continue tracking these quadrats to see over time how long does it really take for them to grow back to their initial amounts. And so again, going all the way to 110 days, we still hadn't seen recovery. This is, again, note the difference in time. This is not continuous time, so take note of that in looking at the axis. These are the number of individuals per 1/4 meter squared quadrat. The green is the control, so this shouldn't change too much through time. The yellow is the cut treatment, and the orange is the cleared treatment, so everything removed from the quadrat. And so initially, no difference between them, which is good, before we cleared them. After we cleared them, obviously, there's nothing left in the cut and cleared treatments. After 41 days, the cut treatments just come right back up. And then with the cleared, much slower to recover. By 110 days, the cleared sort of kept increasing, but still not there. After 326 days, the cleared treatments still weren't at pre-disturbance levels. And then I just monitored them at 606 days. This is just this past December. And while there are no significant differences between the cut and cleared, and what we can say then from this is that it took somewhere between 1 and 2 years for these cleared quadrats to completely recover. So it takes a fair amount of time. Usually you think, again, of algae as being more weedy and popping right back up and regrowing fairly quickly. But it's a fair amount of time for just a 1/4 meter squared quadrat to completely regrow. Another interesting thing is that there are less plants by the end of the experiment than at the beginning. And part of that, I think, is that there is an occurrence of disease, what appeared to be disease, that wiped out a large portion of the meadow. And that happened to hit part of the area where this recovery was going on, where plants died. They turned yellow and they died. So it went from 100% cover, where you couldn't see the bottom, to anywhere from 10 to 0% cover. And of course, that went over half of my experiment in terms of the quadrats that were out there. So that may have affected the time it took, and I think also affected the, it happened between here and here, the total number of plants that were present here versus present here in terms of the overall averages. But that's something to consider, and also interesting in terms of considering growth rates and recovery. And it also goes to show that these meadows are constantly changing in terms of input from multiple factors. You always go and they always look green, they always look like the same number, but they're actually very dynamic in terms of cyanobacterial blooms that occur. Again, this outbreak of disease, urchin recruitment events, all these things impact the densities of these meadows. At the same time that we were doing the clearing experiment, it turned out that we also had an anchor scar that occurred at the same time. This is, again, a 1/4 meter squared quadrat. You can see where the anchor was, and it got dragged. We have to know the exact date of this because I accidentally did it. And it was probably the best and worst thing I ever did. But it was just right at about the same depth and right near the clearing experiment. So it was very, I wish I did 4 more. But it turned out that you can see where the anchor dragged. So it basically cleared off the top of the plants, which is very similar to the cut treatment. And then it cleared out every plant. There's a big hole right here where the main part of the anchor was, and basically removed all the plants, the entire holdfast. So it was a very convenient comparison to our experiment. And by day 105, it turned out everything had regrown that had been cut. So you can't really tell what was there, but you still had a fairly large hole. And after 606 days, about half that hole had filled in. But you can still, there's actually that hole is still kind of there. So, after 1.5 years, you can still see the effects of an anchor scar in these meadows. So that's sort of interesting. The implications of that is that removing the entire holdfast means a long recovery time. The entire plant has to recoup back in that area, regrow the entire thallus and holdfast, and make a new plant. And so what I would think is that if you had an area where there was constant anchoring or constant disturbance of the bottom over long periods of time, it's going to take years for these meadows to recover, depending upon the size of disturbance. It's not like you disturb it and the whole thing just regrows back. It takes a long time. It sort of creeps in from the edges. You have sexual recruitment that has to occur, which is sporadic in these meadows. So it's going to take a while. And the other aspect of this is, in terms of algal, the Halimeda physiology, is how do the growth rates vary seasonally and among depths at 10, 20, 30 meter depths. And so this is going back at these depths, staining 20 plants randomly allocated over 2 25-meter areas at each depth, and then looking at their growth. And so what I'm just going to talk about is the percent of new growth at each of these depths over time. And how we measure growth is with an alizarin stain. So we bag the plants and stain them. New growth, you can tell because it's lightly green compared to the old growth, which is stained pink. Again, you can see here, this is all new growth. The stained portion is pink. And then you just count the number of segments grown over a period of time, which then you can get percent new growth based upon the number of segments that grew compared to the number of segments that were there before. And you can measure then at over an amount of time. So I can